In this study, which is in progress, we introduced a different indicator which is based on the inter-event distances. So the motive of the study is to explore the mechanisms that are responsible for damage, and if we can detect additional indicators in order to compare them with the existing ones, like the ones we mentioned previously, detected from acoustic emissions and pressure-stimulated currents. So at the end, we would like to comparatively consider indications from various sources in order to draw definite conclusions about a catastrophic event that it is upcoming. I will not insist in the techniques used to gather experimental data. We are all familiar with experimental techniques like acoustic emissions or pressure-stimulated currents, or even optical fibers, GPS systems, and so on. There is a revolution in this field due to the rapid development of science. We use data from acoustic emissions and from pressure-stimulated currents. I think I shouldn't insist here. It was described previously. We have data from pressure-stimulated currents and acoustic emissions. Now, what is our purpose now? If we use many acoustic emission sensors, it is possible to detect, among others, the location of the event that produces the acoustic signal. Let us call this position the acoustic source. You need at least 3 sensors to detect the position. I would suggest to use even more, 4 or 5, to have accurate results about the exact position, especially if you have small specimens, because they favor reflections and make the detection of the exact point of the source of the signals very difficult. So if we have n acoustic events, then we can define n-1 inter-event distances between 2 successive events by this very simple function. With the aid of the sensors, we locate the position of each source, and then we can define the distance, the Euclidean distance between the 2 successive events. Then we can split the time series into a number of subgroups in order to calculate mean values of the distance between the acoustic sources. Then we pair each value of the D function with the average time of generation of the acoustic signals of the group, and we can plot the D function as a function of time. Sometimes it is very important to normalize our distances with respect to the dimensions of the specimen. If the specimen is cuboidal, we do not need any normalization, but if we have a prism for which one dimension is much higher compared to the other two, then it is better to use normalization in order to translate the actual specimen into a cube. But the procedure is the same. We just make a division by the dimensions of the specimen. The next step is to check the accumulation of the acoustic sources by defining the position of each one and check whether this position is moving towards a specific point, and if this position is close, approaches existing geometrical discontinuities. If we want a thinner resolution, not just divide the number of events into an arbitrary number of subgroups, then we will use the sliding window procedure. You can see it here. We start with the first subgroup, which is somehow arbitrary, depending on the number of events. If we have thousands of events, then the first group may be hundreds of events. Depends on the accuracy we need. We calculate the function we are interested, whether it is f or d or whatever, for the first group. Then we remove the first event and add the second one. We obtain the second group, and this is sliding until we cover the whole number of the events of the series. We'll discuss data, preliminary data, from 3 protocols. The first one is 3-point bending of concrete specimens. Either the concrete is plain or reinforced with fibers, short fibers, made of polypropylene or polyolefin or steel. You can see here the mechanical response of the protocol. We have the traditional, the expected response of the load. It is very interesting to note that especially for the fiber reinforced specimens, we have not a fracture instant because the specimen is not fractured into two parts. Due to the presence of the reinforcing fibers, we have a slow propagation of a macro crack, which means that the presence of fibers translates the very brittle concrete to a kind of ductile material, we could say. Of course, there is a standard when the conventional time fracture is considered. And you can see here also some data about the mechanical response, the load and the amplitude of the events, the acoustic events, and a magnified view at the very last seconds. It is clear that the vast majority of events and sources appear at the very last second of the experiment. Either it is plain or it is reinforced. The second experiment includes direct tension tests. It's a very difficult protocol. With marble specimens, it is very difficult because marble is very brittle. We have 8 sensors in this case. Again, we have notches because we would like to check, as I mentioned, whether the sources are attracted by geometrical discontinuities. You can see here the mechanical response, the stress-strain curve. Obviously, as we are very close to the crown of notches, we have non-linear response for very early loading steps, while the main specimen is almost linearly elastic. It means that we have a kind of inhomogeneity induced during loading. And again, the majority of acoustic events are generated during the very, very last seconds of the procedure, which makes the analysis of the results very difficult. And the last protocol is a simple uniaxial compression test, again with many sensors. You can see also here the mechanical response, as it is expected for a brittle material, almost linear. We have an onset of non-linearity at relatively high stress levels, and again the axial stress in juxtaposition to the amplitude of the acoustic sources. Now, we apply what I mentioned previously. We divided the time series of acoustic events into a number of subgroups depending on their total number. And you can see in the first picture here the average distance between the acoustic sources. We start with a distance equal to about 14 millimeters. And as the load tends to its maximum, this distance decreases, which means that the sources of acoustic events starts being accumulated. And finally, they reach a minimum. Okay, so a few seconds before the fracture. Here, for example, it's 3 seconds. And then after this minimization, the distance between the sources starts increasing again. It is systematically observed for all specimens of this protocol. Either they are plain or fiber reinforced. We have initially large distances between the sources, and gradually we attain a minimum. Our thought is that when the minimum is achieved, the specimen is at the onset of transition to a catastrophic stage, and fracture is impending. In parallel, we studied the spatial distribution of the acoustic sources. This is the figure we discussed already, and this is the specimen with the notch. Initially, the average position of the sources is arbitrary, and as the load increases, the color code is very helpful. As we attain the minimum of the inter-event distances, the distance from the notch is minimized. Obviously, here we have the onset of crack propagation, and then, as it is expected, the sources move away from the notch, but on the vertical plane of symmetry due to the presence of the reinforcing fibers, which keep the two fragments in contact. And only as we approach the upper limit of the specimen, it starts deviating from this theoretical line, because we have the influence of the punch, which loads and creates locally a very severe stress field. The results are similar for all specimens of this protocol. And now the second protocol, the double-edged not tensile specimens, the conclusions are very, very systematically similar. We start from a distance between the sources equal to about 8 centimeters. It's a very big specimen. That is what is a very difficult protocol. And then it decreases gradually. Pay attention, this is an inverse time arrow. It's very useful to present results if you want to pay attention on the very last loading steps in terms of the time to failure parameter, which is the time minus the fracture time. So this is the fracture point. We are here some 1,000 seconds before fracture. And at about 10 seconds before fracture, we attain a limiting minimum, and then it starts increasing again, exactly as the specimens from the previous protocol. And if we adopt the same color code, you can see also that we have initial accumulation of the sources at an arbitrary point. They are attracted by one of the notches, although the specimen is symmetric, due to inherent inhomogeneities of marble, one of the two will start first. It is impossible to have simultaneous onset of cracking from both notches. We would need a perfect specimen, which is impossible. So one of the notches attracts the position of the sources, and when it starts propagating, it approaches the second notch. And this is systematically observed in all specimens of this protocol. Now, concerning the compression specimen, you can see here that at the initial stages of loading, we have some very large distances between the sources at 35 to 40 millimeters, and we have a rapid decrease at about 70 or 60 seconds before fracture. Here is better the situation. Then the cracks distances, the interevent cracks start increasing again. Why? Because we have the formation of familiar Morse cones, and so the cracks are concentrated within these cones and are moving away from the initial point of generation. As a last step, I tried to compare the results of the distance between the sources to the predictions of the F function, which, as I mentioned, is the function describing the frequency of generation of hits or of acoustic sources, and the energy of the acoustic events and the energy of the acoustic sources. I think it is amazing that at the very first steps of loading, both the F function and the energy are almost zero, and only as we approach the point of minimization of the event distances, both functions start increasing rapidly. Perhaps someone could say that 3 seconds is a very small window, but we have to improve it, and we are working in this direction. Now, skip these details, and let us compare the results of the acoustic data concerning the inter-event distances with the results obtained from the next technique, the technique of electric current. We have plotted here the electric current for the first notch and the second. The red notch is the one from which fracture started, and we plotted here the electric current and the function describing the frequency of generation of hits. We have two functions now because we have two electric pairs. We have electricity generated at this notch and at this notch. Obviously, we observe that the electric current starts increasing very rapidly at the notch from which fracture starts. So we have another tool in our hands to predict the notch from which, the geometric discontinuity from which fracture will start. And if you compare the results of the electric activity with that of the acoustic activity, I think that the similarity is striking. We will not need to comment on these conclusions, which means that we have an additional tool in our hands, besides the well-established technique of acoustic emissions, the tool of pressure-stimulated currents, which has an advantage. Not only it predicts somehow earlier the critical point, but it is very cheap. We all know that the acoustic sensors are not very cheap, and if you have to monitor a large structure and you need a few tenths or hundreds of sensors, this is an expensive game. In order to record electric currents, you need just 2 plates of copper covered with, let us say, golden painted, which is very cheap. So this technique is much cheaper, and perhaps it is the challenge to compare quantitatively the data in order to minimize the cost of using exclusively acoustic sensors. We do need acoustic sensors, of course, because it is the most mature and well-established technique, but in order to minimize the cost of its use, perhaps we should combine it with the pressure-stimulated currents technique. So I think that this is the end for the moment being, and the main conclusion is that all 4 or 5 quantities discussed, the function F, the frequency of events, the function P, the energy of the events, the function D, the inter-event distance, the electric current, predict that we can, not predict, reveal that we can predict upcoming failure. Again, as I mentioned in the plenary lecture, the issue is to increase the window. These few seconds before fracture perhaps are not very useful for practical applications. So we need additional data, and it seems that in our next conference in Athens, perhaps we have more reliable results, because as I mentioned, many groups all over the world, and especially China, are working on this topic, either analyzed by means of non-extensive statistical mechanics or natural time, or with traditional tools like the distance between the sources. And let us put a goal that in Athens we'll increase the window at least 2 times. Thank you very much.